The importance of local rings. So we have already seen this, that if X is a variety over an algebraically closed field K, and you take a point small x in capital X, then we have defined the local ring of the variety capital X at the point small x, okay, and so this is the local ring of capital X at small x. Then we have also defined Kx, which is the so called function field of X, okay, and see we have seen that Kx consists of equivalence classes of rational functions, namely functions which are defined, regular functions which are defined not on all of X but on an open subset of X, okay, and of course the equivalence is that two functions are equivalent if they coincide on the intersection of their domains of definition. On the other hand, the local ring is supposed to be gotten by doing the same thing but concentrating only attention to regular functions in a neighbourhood of the given point small x, okay. So and we have seen that Ox, which is the set of all global regular functions on X, this is a subring of course of the local ring of every local ring, and that is contained in the quotient field, and in fact of course K is of course sitting inside regular functions as constant functions, okay, and in fact this Kx is actually the quotient field of Oxx. The quotient field of this is exactly this. In fact if you go to any open set U then which is non-empty, then Kx is the same as Ku and Aux is the same as Oxx, okay. So let me also write that this is also equal to Aux and this is also equal to Ku, where U is an open subset of X, and yes, small x is in capital U, and so local ring does not change if you go to a smaller open set, and the function field also does not change if you go to a smaller open set, because so called smaller open set is actually not so small, okay. Any non-empty open set of a variety is irreducible and in fact it is dense. So what you are throwing out, the boundary is just a very small set, okay. So and we have seen that the local ring already there is a lot of information stored in these things. In fact so I should also mention that this OX, so I should also say that OX is this is equal to AX if X is affine. So that is also, you also have that OX is the same as AX if X is affine, and in that case this is also equal to the quotient field of AX. Of course when I say when I write AX, this is defined only if X is affine, that is X is isomorphic to an irreducible closed subset of some affine space. And of course there are so many other things. Of course if X is projective, we have seen that OX is, this is equal to this, okay. If X is projective, then OX is just K, alright, then because there are no non-constant global regular functions on a projective variety, right. Then we have also seen that see the local ring stores a lot of information, that so in fact the dimension of X, the topological dimension of X is the same as the Krill dimension of the local ring at each of its points, and this is also equal to the transcendence degree over small k of the extension capital Kx. Capital Kx is the function field of X is it's an extension of K, it contains small k. After all, this K is a field, these things this is a finite, I mean this is a K algebra, and this is a local ring, this is a local K algebra, a local ring which is a K algebra, whereas this is again a field, this is a large, and everything is contained in this big field, okay. And small k to capital Kx is a field extension, okay, because it is a bigger field containing a smaller field, and then the transcendence degree of this over this, namely the by that one means the cardinality of a transcendence basis of this over this, okay, which measures the number of maximum number of algebraically independent transcendental elements over small k, okay. That is a measure of the dimension, topological dimension, okay, and the dimension is also shows up as a Krill dimension of the ring, okay. And you also know that this is also equal to the Krill dimension of Ax if, of course this is if X is affine, okay. So already there is so much information, but then the object of this lecture is to tell you that this local ring is really a very powerful thing. It contains it stores a lot of information. So let me tell you the first thing. So it's about the yeah, so all right, so let me talk about first about local rings and morphisms, okay. So suppose X and Y are varieties and F is a morphism of varieties, you know that means that X and Y could be, both X and Y could each of X and Y could be affine or quasi affine or projective or quasi projective, and the fact that F is a morphism means that F is continuous and F pulls back regular functions to regular functions. So so the point is that if I take a point small x here and it goes to the point small y, which is the image of x under F, and you take an open set U, an open set here which contains the point x, and you take well rather I will do it the other way around, let me take an open set V which is a neighborhood of the point y, and let me set u equal to f inverse V, then of course f being continuous, the inverse image of V is an open set, I call that as u, and then of course f factors like this is just f restricted to u, this diagram commutes, okay. And now you have a map from OV to OU, which is actually O of f inverse of V, and the map is just the pullback of regular functions. So the notation is f hash, and what does it do? If you give me a regular function g on OV, what I do is that, I mean what this does is that it pulls back g to f hash g. And what is f hash g? F hash g is just first apply f restricted to u and then apply g. So f restricted to u followed by g. So this is what, so this is just pullback of functions, okay. So so basically what's happening is that giving a g on OV means that you're giving a function from V to k which is being thought of as a1, and you know if there's a risky topology on k, you have a1 and this g is a morphism. So a regular function is just a morphism into a1, so g is a morphism into a1, and then you compose it with this and then you get a morphism like this, and this is precisely f hash of g. This is the pullback of g by f, okay. And the condition for a morphism is that not only f should be continuous, but whenever you start with a regular function on a target, on an open subset of the target, when you pull it back you should get a regular function on the pullback of that open set on the source, okay. That is part of the definition of a morphism. And one of the important things is that what this leads to is that from f this induces a map f hash y which will go from the local ring of y at small y to the local ring of capital X at small x, okay. You have a map at the level of local rings, right, and this map is of course again it's induced by the same thing, namely what you do is what is an element here? An element of the local ring is just an equivalence class of a function which is regular on an open neighborhood of the point y. So you have something like v comma g, this is what an element here looks like, it's an equivalence class where g is a regular function on v, g belongs to OV, and v is a neighborhood of y, v contains the point small y, and what do you do? It's very simple, you simply send it to the class that corresponds to the pullback of that function which is also a regular function. So I take f hash g and I take it on u which is f inverse of v, and I take this pair and then I take the class. So this is how this map is defined. So all I am trying to say is that if you have a morphism of varieties, that morphism induces for every point small x and you take its image in capital Y, you get in the reverse direction you get a morphism of local rings, okay, and you get one morphism like this gives you a whole bunch of morphisms of local rings going in the other direction, okay, one for each point here and its image there, right. So so you have this situation, and now you can see that it's rather easy to see that, you know, if f is an isomorphism, then you also have a map going in the other direction, okay, and that map will induce a map in this direction now, and you will see that if f is an isomorphism then all these maps on local rings are all isomorphisms, okay. So in fact I must tell you that all these ring maps that we are talking about here are not just ring maps, they are in fact K algebra homomorphisms, okay, they are identity on K and they are K linear, okay. So so it's clear if f is an isomorphism then f hash y is an isomorphism for all small y in capital Y, for all small y in capital Y. So you have this is very clear, okay, because you just have to f induces f hash y in this direction, and then f inverse will induce a map in this direction, which will be f inverse hash x, and you will have f inverse hash x will be the inverse of f hash y, okay. So let me write that, since f inverse hash x will be just f hash y inverse, you will get this, okay. So because from this diagram, if f is an isomorphism, G pulls back to f hash G under f, then f hash G pulls back to G under f inverse, okay, it's quite obvious. So but the beautiful thing about local rings is that you can decide whether something is a morphism using the fact that it's a homeomorphism. It's a morphism which is a homeomorphism, okay, that is a topological isomorphism, plus it induces at the local rings isomorphisms. So that's the big fact. So here is the theorem. The theorem is a morphism f from x to y of varieties is an isomorphism if and only if f is a homeomorphism and f hash y is an isomorphism for all y in y. So here is a very powerful theorem that tells you about the power of local rings. So what it tells you is that if you want to check a morphism as an isomorphism, then you first check it is a topological isomorphism, okay, then check at the local rings the morphisms induced at the level of local rings, they are all isomorphisms, then the morphism is an isomorphism. So for the proof of this, you see one way we have already discussed, that if f is an isomorphism, then of course f is a homeomorphism and fy hash is an isomorphism for every y. That is something that we have already seen, okay. We have to prove the other way around, okay. So one way is already done. So assume that f is a homeomorphism, f is a morphism which is a homeomorphism and f hash y is an isomorphism for all small y in capital Y, okay. So what do I have to prove? I just have to prove that f is an isomorphism, which means I have to show that f inverse is a morphism, that is all, okay. How do I show f is an isomorphism? Just by showing that f has an inverse, but f already has a set theoretic inverse because it is a homeomorphism. F inverse is a continuous map, f has the continuous map f inverse, okay, which is also a homeomorphism. I just have to show that this f inverse is a morphism. Once I am done, once I prove that I am done, okay. So we only have to show f inverse is a morphism, but you see f inverse is a homeomorphism, so f inverse is already continuous, okay. So the only thing you will have to check is that it pulls back regular functions to regular functions, okay. How do you check something is a morphism? You have to check two conditions. One condition is that it is continuous. The second condition is that you have to show that it pulls back regular functions to regular functions. So but f is already a homeomorphism, so f inverse is also a homeomorphism, so it is continuous. The only thing I will have to therefore check is that f inverse pulls back regular functions to regular functions. So since f inverse is already continuous, we only have to show f inverse pulls back regular functions to regular functions. I just have to show this, okay. So so what do I do to do that? So you know I have this so you know I have the situation is like this, so here is x, here is f inverse, and here is y. I had to f inverse already, of course, is a homeomorphism. I have to show it pulls back regular functions to regular functions. So what I'll do is I'll take an open subset u here, open subset. Okay. Of course, whenever I talk about open subset, I'm not mentioning it, but I'm only interested in non-empty open subsets. Okay. So then I take f inverse of u, which is actually f of u, which is v, and this is an open subset here, because after all f is an open map, f is a homeomorphism, so it's an open map. So f of u is an open subset. So f inverse of u is just fu, which is just v, and well, f takes u to v. So I have two arrows, one arrow in this direction, which is an isomorphism, topological isomorphism, which is f restricted to u, and I have a map like this, which is f inverse restricted to v. Okay, I have this. What do I have to show? I have to show that start with the regular function here. I have to show that f inverse pulls back a regular function to a regular function. So I'll have to look at OU, which is a regular, these are regular functions on u, and from here I'll get OV, these are regular functions on v, and this is f inverse hash. Okay, it is this, I have to check that this f inverse hash, which is pulling back regular functions by f inverse, I actually show that this have to show that this lands into this. Okay, so so let me do something. If I write like this, then I'm already assuming that it's landing inside OV. So I have to do something. I'll have to write O. So I'll just write maps from v to k, okay, and mind you, I start with a h, which is regular function on u. Okay, so I have h like this, it's a morphism into a1. Okay, and what I'll have to do is the pullback of h under f inverse hash is just composition of h with f inverse. Okay, so what I'll get is I'll just have to apply I'll have to apply f inverse to v. I have to take f inverse restricted to v. I have to first apply that, and that will take me from here to here, and then I have to apply h. This is what it goes to. Okay, and now so the composition is this. So it's a map like this. This is f inverse hash of h. Okay, it is just this f inverse followed by this h. I pull back the regular function h to a function on v, and I'll have to show that this function on v, this function from v with values in k, is not just a function. I have to show it's regular. So the first thing that I want you to notice is that it's not just a map from v to k, it actually goes into the subset of maps continuous for the Zariski topology from v to a1. Certainly it's a continuous map, because it's a composition of f inverse, which is a continuous map, and the map h, and the map h is continuous because, mind you, any regular function is continuous. after all a regular function is a morphism into a1 and a morphism is always continuous, okay, and so there is a composition of continuous functions, so it is continuous, right. But what I have to show, so this is not just here but it actually belongs here, but what I have to show is that it actually belongs even in OV. This is what I will have to show. I will have to show that this is actually here, I have to show it is regular, alright, and that is a smaller subset. Not every continuous map is a regular function, okay. So but then the point is, how do I check something is regular? How do I check a map is regular? See, the notion of regular is something that is very local, okay. So to check that something is regular, I just have to check it at every point, right. So you know, so I will have to just check that this function is regular at each point of V, that is all I have to check, right. And so for that we do the following thing, you know, so now comes this business about so now comes this, now I will have to use this hypothesis that F inverse hash, I mean this Fy hash are all isomorphisms for every small y in capital Y. I will have to use this. So what I will do is I will start with a y in V. So I have you start with a small y in V and you take small x in U with f of x is equal to y, which is the same as saying x is f inverse y, okay. So small y goes to small x and this y is fx, f of small x, okay, and of course I have chosen y in V. So you know I have this OV is regular functions on V, then I have this OYY which is the same as OVY, because as I told you the local ring does not change if you go to a smaller open set, alright, and you know this is the regular functions are sitting inside the local ring of course, okay, and on the other hand I have also OXX, O capital X small x, which is a local ring of capital X at small x, is the same as OUX, because after all U is a smaller open set which contains a point small x and the local ring does not change if you go to a smaller open set, and this is also contained inside this, okay, and the point is that this F inverse hash induces F inverse hash x, yeah, so F inverse so I still have to say that F inverse is yeah, so I need to do something here, so I will not use this, I will rather use the map that is in the other direction which is given to me. What is given to me is that Fy hash is an isomorphism. So you know, so there is a map like this which is Fy hash, okay, and this is an isomorphism, this is given, it is given that this is an isomorphism, alright, it is given that this is an isomorphism, and mind you this Fy hash is induced by F which is actually going in this direction, okay. So it is given to me that this you know this Fy hash is an isomorphism for every small y, okay, I have to use that. So well so what do? I do the following thing. So you know, see this h is a regular function on U, okay. Since h is a regular function on U, it gives me a germ at the point small x, namely what is the germ? The germ is just you take the equivalence class U comma h, you take the pair U comma h and take its equivalence class, that's an element here. Okay, this is how you have a map from the regular functions on an open set to the local ring at a point on that set, namely you take this pair consisting of the regular function and that open set and take the equivalence class, and such equivalence classes up to equality on intersections is what constitutes the local ring at the point. Okay, so I have this, but then you know f hash y is an isomorphism, so this comes from something here and that is here, that is in the local ring. Therefore what it means is that so let me write this down, since f hash y is an isomorphism, there exists a germ here which goes to that, and how is a germ here represented? A germ here is represented by a regular function on an open subset of y. Okay, so so what I have is, well, I have there exists w comma let me use some other symbol, I've not used g, let me use g. There exists w comma g which is a germ, an element of the local ring of capital Y at small y, which is of course the same as O, if you want, O v y. So you know in that sense w can, I can even think of w as sitting inside v, such that in fact this is unique because it is an isomorphism, such that f hash y of this w comma g is this class u comma h. Okay, so this happens just because this has a pre-image here, this is an isomorphism. Okay, so what I get is I have a w comma g here which goes to this under f hash y, because f and that w comma g is of course a unique germ because it's because f hash y is an isomorphism, K-algebra isomorphism. Now what you will have to notice is that see if you now look at this g is defined on w, and this w is an open, see after all w is an open subset of y, and in fact it contains the point small y, so it will also intersect v. You could even think of w as an open subset of v, but in any case if you want to think of it as an open subset of y, you can always intersect it with v. So what happens is that you have O of w intersection v, you have this, okay, and you have this fellow here, namely you have this g is a regular function there. Okay, and what's happening is that well, you know, if I take the image of this under f inverse, okay, then I'll get f inverse of w intersection v, okay, and I'll get O of this, and this will be f hash. I have this f hash, okay, this f hash, you see f is in this direction, so f hash will be in this direction. So f will go from f inverse w intersection v to w intersection v, okay. So f hash will be pulled back of regular functions in the opposite direction, namely a regular function on w intersection v goes to a regular function on f inverse of w intersection v, right. And so you know if you take this g here, what will happen is that I will get f hash g, that will be here. So this f hash g will be a regular function on f inverse w intersection v, and of course f inverse of w intersection v will intersect u anyway, because x is in w intersection v and x is also in u, okay. And the point is that see this, it is this f hash which actually induces f hash y, because you should remember that the morphism, the the K algebra homomorphism, the local rings are induced from the given morphism by pull back of regular functions. So the point is that you have a commutative diagram like this. So you have, if you go to the local ring of x at small x and you go to the local ring of y at small y, then this is sitting inside this, this is sitting inside this, and you have this f hash y, and this f hash y is precisely going to take, see, the germ of f hash g, see, to whatever it is going to go to, okay, that is the same as taking the germ here and applying f hash y, okay. But if I take the germ here, g is going to w, it is just going to this germ, okay. So it is just going to the germ of w comma g, okay, and that, so maybe I'll write a little below so that I can have more space. Well, this guy is really going to go here to germ of w comma g, and this fellow by our definition of f hash y is going to go to u comma h, germ of u comma h, and that is precisely what this f hash of g has to go to, okay. F hash of g has to go to u comma h, alright. So so the moral of the story is that you see f hash of g and see, but f hash of g will go to what? F hash of g will go to w intersection v intersection u comma, so let me write that down correctly. So what you will get here is, so let me have some more space to write. So what is this going to go to? It's just going to go to if you want w f inverse w intersection f inverse of w intersection v comma f hash of g, and that is the same as this fellow here u comma h as germs, because this is what goes to that, okay, and you have something like this, this diagram commutes, okay. Now so the moral of the story is that this f hash g and h coincide when are two germs the same, when are two germs the same, when are the germs of two pairs the same? By the definition of the local ring, the two pairs define the same germ if the functions coincide on an intersection. So what this tells you is that f hash of g coincides with h in a neighborhood of y of x, okay. F hash of g coincides with h in a neighborhood of x, that's because these two germs are the same, alright. But then but what is f hash of g? F hash of g is just you apply you first apply f and then you apply g. So f hash of g is just g circle f, g circle, of course f restricted to f inverse v intersection w. This is what f hash of g is. F hash of g is just the pullback of the function g. So g is a regular function on w intersection v, and f takes f inverse w intersection v to w intersection v, and you first apply f then you apply g. The composition is precisely f hash of g. So what you are saying is that g circle f restricted to f inverse w intersection v coincides with h, but that is the same as saying that because f is a homeomorphism, it is the same as saying that g coincides with h circle f inverse v in a neighborhood of y. So this this implies that g coincides with H circle F inverse restricted to V in a neighbourhood of Y, because you know F is a homeomorphism, okay, on whichever neighbourhood F hash G coincides with H. If you apply F inverse on the right, you will get that G will coincide with H circle F inverse V. So you see what is F hash G? F hash G is G circle F restricted to F inverse W into F restricted to F inverse of W intersection V, okay, that coincides with H, okay. Then if you apply F inverse on the right, you will get G coincides with H circle F inverse restricted to V in a neighbourhood of Y, because you just apply F inverse, okay. So what have we proved? What we have proved is that this H circle F inverse V in a neighbourhood of the point small y is equal to a G, but what is G? G is a regular function. So what you have proved is that this function that is defined on the whole of V is at every point equal to a regular function. That means it is locally regular, and a function that is locally regular is regular because the definition of regularity is local, okay. Therefore we are done. So this implies that H circle F inverse V is actually in OV, okay. So that ends the proof. So let me repeat. What we did is we started with a regular function H on U, and then we pulled it back. We wanted to show that this is a regular function on V, okay, but what we end up proving is that for every point small y of capital V, if you give me any point small y of capital V, there is a neighbourhood where this function is equal to a regular function. That means this function is locally a regular function. A function which is locally a regular function is regular because the definition of regularity is local. This function is already continuous, okay. So we have proved that F inverse hash pulls back regular functions to regular functions. We already know it's continuous, therefore F inverse is a morphism and we are done, therefore F is an isomorphism, okay. So what you must understand is that you must realize that to check that something is a morphism, there are two steps. One is to check topologically that it is continuous. The second thing is you have to check that it pulls back regular functions to regular functions. But the point is that the checking that it pulls back regular functions to regular functions can always be done even at the level of local rings. That's essentially the idea. So to check that a morphism is an isomorphism, all you have to check is that the morphism is topologically an isomorphism, namely a homeomorphism, plus you must check that it induces isomorphism at the level of local rings, okay, at every local ring, okay. So that's the power of local rings. So from now onwards, whenever you see a morphism which is topologically a homeomorphism, what is an easy way to check that it is actually an isomorphism? You just check that at local rings it induces isomorphisms. And mind you, I told you that there are morphisms which are topologically isomorphisms, that is homeomorphisms, but for which the inverse map is not a morphism. There are morphisms like that, they are bad morphisms, okay. So just because a morphism is a topological isomorphism need not mean that it will have an inverse morphism. It need not be an isomorphism. It may be, so a morphism can be an isomorphism in the topological sense between two varieties, but it may not be an isomorphism in the sense of varieties. It may not be an isomorphism of varieties. So you can have two varieties that are topologically the same, but as varieties they are very different, okay. Okay, so this is one important fact about local rings. The next thing that I want to talk about is about the other important fact about local rings is you know So here we have seen that somehow the behavior of the morphism is controlled by all the ring homomorphisms that it induces at the level of local rings, right. That's the whole idea. Now for example, the fact that this is an isomorphism is captured from the fact that all the local ring at the local ring level it induces isomorphisms, okay. So the behavior of morphism at the local ring level controls everything, okay. Now that's at the level of morphisms. What about the level of regular functions? So let me make a very simple statement which seems tautological. So if you have a rational function on a variety, okay, by definition a rational function on a variety is an element of the function field. It's a regular function defined on an open set. Of course there could be a locus where it is not defined, okay, namely the complement. There could be some closed set where it is not defined. Now when do you conclude that a rational function is a regular function? So a rational function is an element here. If capital X is a variety, a rational function is an element here, and when do I conclude that it is here? Okay, when do I conclude that a rational function is regular? Which means this means what I am trying to say is I am trying to say that the rational function is actually defined everywhere. Okay, when you say rational function, a rational function is only a regular function that is defined only on an open subset. It need not be defined on the whole variety, okay. But if you ask the question when is a rational function actually regular, the answer to that is the following: to check that something here is here, it's enough to check that it is here in every local ring, okay. So it's a very nice result to check that a rational. So the idea is like this. The idea is that if you have a rational function and if it is in every local ring, the fact that it is in every local ring means that at every point in a neighbourhood of the point it can be extended to a regular function. That means you can extend it to a regular function everywhere. Therefore it should be a global regular function, so it should be here, okay. But then how does one prove it accurately using commutative algebra? We will do that in the next lecture.